welcome back once again, guys, okay? So, in our first, what we looked at, we had a coin and a die, and what we wanted to do was to calculate how many possible outcomes are there if I roll a die and also a coin simultaneously. We said a coin has two possible outcomes, a head and a tail, but a die has 6, and we multiply that by 2, which is 2 times 6, and we got that is 12. Are we together? So we had 12 possible outcomes if we do the two simultaneously. Okay, fantastic. So what we're going to look at now is to go and look at the fundamental principle of counting. Okay, what does that look like? So it's the fundamental counting principle. What is this fundamental counting principle? We can use list, table, and tree diagrams to work out the numbers of outcomes. Okay, are we together? Like listing, it was easy in the first example because for a coin, we only had 2 possible outcomes, and for a die, 6. So we can just list and see that actually there's 12 possible outcomes. But that can be difficult, especially if that set is large. Okay, so we have to find a way actually to do that in an efficient way. So using tree diagram can work, tables also can work, but this is only feasible. It's feasible for an event with few outcomes like the previous one. We had few outcomes because we had 2 possible outcomes for a coin and 6 for a die. That was okay, but for a large one, it's quite difficult. Okay. So when the numbers of outcomes grows, it is not practical. It's not practical to list the different possible outcomes. It becomes impossible. We could list in the first example if we have a coin and a die. We can list the possible outcome. We can say, okay, if I roll, I can get 1 and tail. That's 1 possible outcome. We can have 6, probably what? A tail. So it's easy to list that. But large becomes difficult for us to do this. Okay? It's not really efficient if we have lots of possible outcomes. So we'll have to use the fundamental counting principle instead. We have to use, what is this fundamental principle of counting? Let's look at that. It states like this. The fundamental counting principle states that if there are NA objects, are we together? Okay. In event A, and NB outcomes in event B, then there are N times B outcomes in event A and event B combined. What does that mean? I mean, it looks more mathematical, but let's break this down. If we have a die and a coin is event A, a die is event B. Are we all together? So, the possible outcomes for a coin, it's what? 2, it's a number of event 2, and for a die, 6, which is our NA times N B, is the number of A and numbers in B. Are we all together? Fantastic. Okay. So, if we apply this principle, the fundamental counting principle, for our previous example had a coin and a die. We can easily calculate the number of possible outcomes by multiplying the number of possible dice rolls, which is what? 6, okay? With the number of what? Tossing a coin, which was 2. So the number of possible outcomes is 6 times 2, which is 12. That's the fundamental principle of counting. Are we together? Great, fantastic. Now, let's look at this. So another way of stating the fundamental of counting principle is this. This another way. If there are m possible outcomes, are we together? For event A, and n possible outcome for event 2, then the total possible outcomes for both events is m times n. That's the same thing. Similarly to the previous question, the number of possible outcomes for a coin is 2. The number of possible outcomes for a die is 6. Then m times n is 6 times 2, which gives us 12. Are we together? Fantastic. So let's look at an example here. A meal can be made up as follows. So here we have to choose a meal. So choice 1, it's meat, fish, chicken. Then choice 2, mash, you have mash there, chips, baked potatoes, rice, and vegetable. So the question is, how many different meals can be made using these choices? Okay, what does this mean? Can I take meat, mash, and chips? No, no, no. I have to select one from choice 1 and one from choice 2. Can I take meat, fish, then mash? Not allowed. You can't do that. But I can take meat, mash, that's okay. I can take meat and chips. I can take fish and baked potatoes. So you have to select one option from choice 1, another option from choice 2. So how many choices are there? Can you think about this? Okay, so if you look at this, we can try write some of the choices. Okay, so let's say, I'll say meat and mash, that's one choice, okay? But that will take time. Meat and mash is one, meat and fish, it's another one, meat and baked potatoes, another one, meat and rice, another one, what? Meat and vegetables, that's another one. Fish and mash, fish and chips, fish and baked potatoes, fish and rice, and fish and vegetable. Yes, that's what we can do. But now, if we apply the fundamental principle of counting, so we're going to look at in choice 1. We have how many meal choices? In choice 1, we have how many choices? We have 3. And in the second choice, we have how many? Let's look at that. It's 1, 2, 3, 4, 5. So 3 times 5. Are we together? In the first choice, we have 3. Are we together? In the second one, we have 5. Then we multiply the 2, and we get this 15 different meals. Are we together? So you can try this without using the fundamental principle of calculus. You'll see that you'll get 15 choices which are available. Are we all together? That makes sense? Okay, fantastic, great. So we apply the fundamental principle of calculus by saying in choice 1, there's 3, in choice 2, there's 5, and we multiply the 2, and we get 15 choices. Great. Looks easy, but there's so many choices there. Now, so what are we going to do now? We're going to look at choices with repetition. Okay. So, this is choice with repetition. What does it mean? Repetition, what does repetition mean? Okay. If I have to design a password for my cell phone, if I have to create a 4-digit password, I use 5555. I'm repeating 5. If I'm using 5666, I'm repeating 5 and 6. But ask yourself, is that password secured? How do you make that password difficult to crack or for someone to unlock your cell phone? So if I use different digits, it'll make it difficult and probably include some of the variables, some of the letters. It'll make it even more difficult. Okay. So what we're going to do here is count with repetition. What does it mean? Okay, we'll look at that. Let's see. When you have objects to choose from, so when you have to choose from, and you choose them from r times, the total number of possibles is what? Is n times n times n times n times n times n all the way. Okay, let's use numbers to make this easy. Let's say I have to create a password, 4-digit password, but I'm repeating digits. How many numbers do we have? 0 to 10 to 9. So we have 10 numbers. So if I have to repeat the first digit for my password, how many chances are there? It's 10, because I can repeat. For the second one, I can still use 10. For the third one, I can still use 10. For the fourth one, I can still use 10. So what does that mean? We're repeating some n object times n object times n object. If you multiply this r times, we'll get n to the power of r. That's the meaning of that. Are we all together? Okay. Fantastic. Okay. Hope this makes sense. So with the password, let me look at the password. Let's take a password. Let's use numbers. So let's say I have a password to design. And I have to use numbers. So this will represent what? 10, agreed? Because there's 10 numbers, and this will represent 10, this will represent 10, all the way to the power, this will be 10 to the power of r, if I have a large password. Okay. Okay, now let's look at another example, but this example differs slightly from the previous one, because the previous example, we only had 2 choices. We could choose some meat or something, and with a starch. But this example, we have 3 choices, okay, which we have to choose meat, fish, chicken. And the second choice, we have to choose mash, chips, baked potatoes, rice, or vegetable. What is added here? It's a dessert, ice cream, cake, or jelly. Are we together? So now the question is, how many different meals can be made using these choices? Okay, fantastic. So the previous one, I could do that from my head because I only had choice 1 and choice 2. And choice 1, you had just 3 choices. I could do that from my head. How we got that 15, I could have done this and said meat. Meat can go with mash, chips, baked potatoes, rice, and vegetable. So meat has how many combinations? 1, 2, 3, 4, 5. So meat, I can choose 5. Fish, similarly, I could choose mash or chips, baked potatoes, rice, or vegetable. So there's also 5. Chicken also, there's 5. Hence we got the 5 for that, and the 5 for that, and the 5 for that, which gave us 15. But by the fundamental principle of counting, we don't have to physically count and combine this and combine this. What we can do is what we did, we just choice 1, multiply by choice 2, which is 15. Now we have 3 choices. Can we apply the same principle? What do you think? Okay, let's look at this first. So here, meat, I can take meat, mash, ice cream. That's 1 choice. This looks more difficult if I have to do it from my head without using the fundamental principle of calculus, of counting. Because meat, I can take meat, mash, ice cream. But also I can take meat, chips, and still ice cream. How many choices are there? Can we really find all of them without using the fundamental principle of counting? I think that will be difficult, but we can. But if you apply the fundamental principle of counting, what we can do is choice 1. How many choices are there here? We have 3. So for choice 1, we have how many choices? 3. So we'll have to say 3 because we have meat, fish, chicken. For choice 2, we have 3, 1, 2, 3, 4, 5. Then we have 5 choices. We multiply by 5. And choice 3, we can take ice cream, cake, or jelly. So we have 3 choices. And we multiply that. 3 times 5 is 15. 15 times 3, we have 45 choices. So what we did is choice 1 times choice 2 times choice 3. Okay, so we'll end from here, and we'll see you shortly.